Good evening, everyone. So let's solve today's Leetcode problem. Smallest subtree with all the deepest nodes. Let's read out the first line. Given the root of a binary tree, the depth of each node is the shortest distance of the root. What do they mean by this? So the depth of each node, let's say we take 5, the depth of it from the root is 1, which is the distance from the root. Likewise, the depth of node 6 is 1 and 2. Likewise, the depth of root node 7 is 1, 2, and 3. So that's what they mean by the depth of each node is the shortest distance to the root. Now they're asking return the smallest subtree such that it contains all of such deepest nodes in the original tree. Now, what do they mean by the deepest nodes? Deepest nodes are the ones which have the greatest depth, which is, let's take the nodes 7 and 4. What is the depth of 7? 1, 2, and 3. And also in the same way, the node 4's depth is 1, 2, and 3. And so they're asking return the smallest subtree such that it contains all of such deepest nodes in the original tree. The smallest subtree, remember, it's a bottom up of approach, right? You cannot go from top. See, even root 3 also contains 7 and 4 as its subchild, but that is not our solution because we want the smallest subtree, which is 2, right? So 2 is the smallest subtree which contains 7 and 4. And why 7 and 4 has to be contained in that is because it's the deepest nodes in the tree. 7 and 4 has got the depth of 3, right? So that is our solution. How do we do this, right? There are multiple approaches, right? You can either do it using depth first search or BFS. Let's say you do it with BFS, right? In the first layer, there is one node. In the second layer, two and four. Likewise, again, two. Now we do know that one, two, three, four. In the fourth layer, we have got all of the nodes which has got the maximum depth. We could either track down their ancestors and go back until you find only one node, right? Let's say we would track down 7, you go back to 2. You track down 4, you also go back to 2. So until you get only one of the node, you keep traversing it back. But it's easier to say it, but to code it up, it obviously becomes complicated. But the another solution to this is DFS, right? Depth first search. Why do we use depth first search? Even though it seems pretty complicated here, but to code it up and the intuition to understand the problem is much simpler, right? So what do we do is we recursively go through all of the nodes from the top, and then as we go to the end, we return back the node along with its subtrees, the height of the subtree, right? So if the node, we take 2, right? So if we have 7 and 4, and this is our solution. How do we know that 2 is our solution? That is our depth, right? 7 and 4 are equal, right? 3 and 3, because the distance of 7 from root is 3, distance of 4 from 3 is 3. So we do know that the subtrees of 2 are equal in length and they are maximum 3 and 3. So this could be one of our possible solution, but this is a bottom up approach. We are going from bottom to the top. So there might be some solution here which we still don't know. Assuming that we are yet to find the solution, we go from bottom to up, right? So among this 2, 7, and 4, we are returning the node 2 with the height as 1 because this is the height. Instead of depth, we are coming from the bottom and we call it as height. So let's say we call that as height. So whereas node 6 has null and null, right? To the left it's null, to the right it's null. This can also be potentially our solution. We don't know that, but the height of this node is 0 here because there is null and null. What do we know as the best probable answer among 2 and 6? 2 is our probable answer. So we send 2 up to this recursive iteration. Now, among in the 5, let's say the height of the left tree is 1, whereas the right tree is 2. So probably our solution lies somewhere here. But we do know that 2 is our answer, right? So how do we exactly send 2? Is because we have got our height also sent back to the recursive step, which is 2, whereas this side it's only 1. We return back the maximum height of the node back to its parent child, right? 5. And likewise, here we return back. If it's unequal, right? We only return back 2 if it's unequal. If both of them are equal, that means if 6 had some other nodes here, 6 had some random nodes x and y, that means all of this x, y, 7 and 4 were having the ancestor as 5. So if both the sides are equal, you send back the current node. But if the right subtree is greater than left subtree, you carry on continuing with 2 itself and send back with increased height because the height increases here, obviously. But in this case, we don't have x and y like I discussed here. So we are returning back to itself, but with an increased height with 1 plus 1, 2. Likewise, here also it's the same way, right? When you recursively solve both left and right side, the right side gives out the height as 2, whereas left side gives out the height as 3, right? So at the same time, if it's unequal, you keep returning back whatever you found it as equal previously, right? So 2 has equal length, 7 and 4. So you're still sending back 2 to the top, right? 2 to the top, it goes back here and here also at 3, you notice that 1, 2, 3. The height of the left subtree is 3, whereas the right subtree is 1 and 2. So here also we don't get 3 as the answer because it has got two uneven subtrees to the left and right. So we still carry this itself to the top, which is 2, 7, and 4. So the answer here in the first example is obviously 2, 7, and 4. So how do we code this up? And I'll try to code this up in Python and using the DFS approach, right? So first I'm trying to define the DFS, and if the base case is if it's not a node, let's add an e to the end. If not a node, we return a tuple value, right? Which has got none and also the height of the tree. So basically, what is this base case? Is when you reach the end of the leaf node, you are first returning something in the form of tuple, right? The node, which is none, and the height of it, which is 0, right? Okay, so here's where we start. And then we recursively find okay, when you start from 3, you recursively find all the nodes to the left and also all the nodes to the right. So how do we do it? And node left. Okay, I'll just node left and nodes height, right? Or left height. Left height. You're just trying to call it recursively, which is node dot left. Same way you're doing it to the right thing, right height equal to DFS of node of right. And now we have got two conditions. Like how I said, if it's equal here, the subtrees of 2 is 7 and 4, which are equally deep, right? 7 and 4 are both having 3 as the depth, and which is the maximum, right? So how do we write the base? How do we write the condition for it? If left height is also equal to right height. So we are basically returning the node itself and the height of it plus 1. Now, why do we need plus 1 here? Because when you're returning back to the previous recursion step, the height increases by 1. So you're always trying to send back one height more than the current height. In this case, both left and right height are same. So I'm just using the left height here. Whereas the second scenario is if left height is greater than right height. So you're returning the left node, right? Left node, which is node left. And at the same time, left height plus 1. Um, else. Now, what if the right height is greater than left height? We return the right node along with the right height plus 1. And I hope I've covered everything. Now there has to be a base, we need to call DFS initially, right? And store what node is it exactly, which is DFS on root. This is where we are calling it. I hope this is the solution. Let's check this out. All right, these are the test cases. Let's try submitting it. All right, we have passed with 100 percent runtime. Okay, we are done with the problem. I mean, you could also solve it using BFS or other approaches of DFS, but hopefully this is the most optimal one. Thank you for watching. I'll see you next time.